So welcome to part 4 of Physics Paper 2. And I'm just going to go straight into it because I've introduced myself, so we'll go straight into it. So let's look at question 7. So figure 14 shows the vertical forces on an aeroplane. Okay, so we've got 8.4 kilonewtons upwards, that would be the lift, and 7.5 kilonewtons downwards, that would be gravity. So use information from the diagram to determine the size and direction of the resultant vertical force on the aeroplane. Okay, so that's actually nice and easy. The resultant force, okay, so all that is 8.4 minus 7.5, and that would be 0.9. Okay, and let's think, so that's the greater one, so that'll be upwards. Okay, that's nice and easy. 2 marks for that, 0.9, and you can just say up, upwards, up. Okay, and we'll draw an arrow as well too. Okay, the aeroplane is descending, that's going down. Figure 15 shows a diagram of the resultant vertical and horizontal force on the aeroplane as it is descending. 300 newtons down, 400 newtons going that way. Complete the diagram to show the resultant of these two forces. So you've got a triangle of forces here. Okay, let's draw. So that's the resultant will be going that way, like that, resultant. Okay, that's 1 mark. Let's draw one thing. The mass of the aeroplane is 730 kilograms. Calculate the change in gravitational potential energy of the aeroplane as it descends from 1,300 meters to the ground. Gravitational field strength can be taken as 10 newtons per kilogram. That's nice and easy. So it's GPU, nice and easy one. Gravitational potential energy, remember it's in joules, M times G times delta H, because a change in height. Okay, so mass 750 kilograms times 10, that's gravity. Okay, times the change in height, 1,300. When you get a big number, you can tell from this. So 9,800,000 joules. Okay, that can actually be shortened into, that'll be a perfectly acceptable answer. We're just going to shorten it down into standard form. 9.8 times 10 to the 6 joules. Okay, nice and easy. That will be, you could write that, that's fine. So don't worry too much if you don't know how to do standard form. That's fine, just look at the full marks. Number 7, the aeroplane is powered by an engine that burns fuel. The fuel supplies a total of 6,500 kilojoules to the engine every minute. The efficiency of the engine is 0.7 or 70%. Calculate the power outage of the engine. Give your energy in kilowatts. So 6,500 joules every minute. Okay, let's write that down first. But it's only 70% efficient, so we can just straight away times it by 0.7 to get the energy, 4,550 kilojoules per minute. Okay, calculate the power output, and the power, okay, power equals energy over time. Okay, so we get 4,550, what we calculated before, kilojoules. Right, so minute is 60 seconds, so we want it in seconds, 60 seconds, that is just per seconds. Okay, and we get 76 kilowatts. Okay, 76 kilowatts. That's the answer there. Let's do the next thing. Let's go. So Explain why the efficiency of the engine is less than 1 or less than 100%. Okay, so nothing, there's no system that is 100% efficient. Okay, and it's actually impossible to get over 100% efficient. So it's always going to be the case. So output energy is less than input energy, because it always is. So output energy is less than input energy. Because some input energy is transferred to non-useful forms. Okay. That is always the case with everything. A question is asked for anything else, that would be the same. Okay. Ooh, electrical things. We talked about that yet. So a resistor is connected to a power supply. The potential difference across the resistor is 6 volts. Which of these corresponds to a potential difference of 6 volts? So, potential difference across this. Okay, so it's asking what the units of the volt really are here. So is it 6 joules per ohm, 6 amps per coulomb, 6 joules per coulomb, or 6 amps per ohm? So the only one there is C, joules per coulomb, because 1 volt, let me just write. So 1 volt equals 1 joule per coulomb. Okay, that is the definition of a volt, is 1 joule per coulomb. Okay, the resistor remains connected for a period of time. The current in the resistor is 200 milliamps. A total charge of 42 coulombs flows through the resistor. Calculate in minutes the time taken for this charge, so this amount of charge to flow through the resistor. Okay, so this equation, okay, is Q equals I times T. Q is charge, coulombs. I is current in amps. And T is time in seconds. Okay. Total charge of 42. So 42 coulombs. I'm going to put the units in for a moment. Okay. I times T. So I is in milliamps. So 200 milliamps. So we're going to have to change that into amps. So we divide it by 1,000 times by the time. So we don't know the time. Okay. So we have to rearrange it. T equals 42 times 1,000 over 200. Right, okay. So 200, okay, times 60, okay, for minutes. It's 3.5 minutes. 3.5 minutes. Calculate the total energy transferred by a 6-volt power supply when a charge of 42 coulombs flows through the resistor. Total energy transferred. Okay, so we're going to use E equals V times I times T. Okay, so again, there's no rearranging going on. Okay, voltage, 6 volts. Okay, total energy supplied through the resistor. So it was at 200 milliamps. So this time, I'm going to write 200 milliamps, 200 times 10 to the minus 3. Okay, and the time Okay, so the time taken there was, so let's calculate one. So it's 3.5 minutes there. Okay. Let's think about how many seconds that's going to be. Okay, so 42 times 6 equals, let's calculate total weight transfer by when a charge of 42 kilograms flows through the resistor. So time in seconds. So it's 3.5 times 60. Okay, put that into our calculators. We'll get 250 joules. Okay, there. Okay, the resistor becomes warm while there is a current in it. Explain why the resistor becomes warm. So, why a resistor becomes warm? So any component becomes warm. These are collisions. Okay, collisions between the electrons and the metallic lattice. Okay. Causes kinetic energy to be transferred to thermal energy. Okay, next question, number 8. Oh, no, quite number 8, sorry. Quite B. Then that's C, sorry, still number 8. So figure 16 shows a cardboard tube with a wire coming out from each end, P and Q. There are two 10-ohm resistors inside the cardboard tube. A potential difference of 6 volts is connected to P and Q. There is a current of 1.2 amps in the wire. Deduce, so that work out, how the resistors have been arranged inside the carbon tube. So two 10-ohm resistors, potential differences, write this down, what we have. So potential difference is volts. Okay, so 6 volts. Okay, current 1.2. Okay, so if they are, so let's look at Ohm's law first of all. So we've got to work this out. A little bit of a puzzle. V equals IR. Okay, so let's rearrange to make R the subject there. R equals V over I. But if the resistors are in series, they just add together. So if in series, okay, so the resistance, so V over, so voltage 6 over 1.2. So we get our calculators out. So let's just calculate this. So calculator. Okay. 6 over 1.2. 5. 5 ohms. So if they were in series, that would be 20, wouldn't they? They'd add together. So if in series, R1 plus R2 equals 20, so they must be in parallel. Because that 5 ohms is actually less. So if you actually get a resistance that's less than the actual amount, okay, of say, for example, they're 10 ohms, you actually get a resistance that's less than both of those, it must be in parallel. So here we've got resistance of using our So obviously, if they're inside the tube, you don't know how. So if they were in series, you'd get a 20 ohm resistance. But if we get an actual resistance that's less than both of those, we actually it must be in parallel. You should remember series. This is a recap. R1, so R1 plus R2, so that's R total equals parallel. Okay, so R1 over R total. So we have to do this whole thing in this question because they must be in series or parallel, because only two of them. So 1 over R1 plus 1 over R2. Okay, so they must be in parallel. So I'm going to stop this video. Okay, I'll see you in the next part.